and welcome to today's webinar, Designing Fault-Tolerant Applications.
So today we'd like to talk to you about building fault-tolerant applications using the Amazon Web Services. Much of the material in today's presentation is drawn from a white paper of the same name that we published last year. This white paper is available in the new AWS Architecture Center, and we will give you a link to that at the end of this presentation. Our goal today is to share our knowledge and our best practices, and we want to make sure that we impart that knowledge over to you, and we'd also like to hear back from you. So as you listen, please feel free to contribute your observations through the comments, and later in this week we will be emailing you, and please feel free to reply and let us know your comments and any best practices that you've discovered that you would like to share with us and with your peers as well. So today we're going to start out with an AWS feature review to make sure that that you have a good understanding of all the different AWS features that you can use to achieve fault tolerance. We're doing this primarily because we realize that we have been rolling out new services and new features very, very quickly, and sometimes it seems as if you might blink and miss something. We want to make sure that if you happen to take a day or two off, that you didn't miss an important aspect of AWS. We're going to spend a lot of time on architectural guidance. We're going to tell you the things that we have learned over years of building highly scalable, highly available applications, how to engineer fault tolerance into those applications. We're going to talk about some hints and tips and kind of additional observations. We're going to point you to some additional resources where you can go further than what we've had time for today. And then we're going to have time at the end for your questions, and then the three of us will jointly answer your questions. So in addition, one of the duties I have as the evangelist is to write the AWS blog that perhaps you read. And I do know that we do put out a lot of services and a lot of new features very, very quickly. And it is possible to, if you turn your head for a bit, sometimes you can miss an important feature. So let's start out just by really reviewing the different aspects of AWS and making sure that we're all on the same page for the rest of the presentation. The first thing we should talk about is the fact that some of the services in AWS, you can think of those as inherently fault tolerant and highly available, where fault tolerance and durability is engineered into the service at the base. So when you build applications using these services, you don't have to think in terms of engineering additional durability or fault tolerance on top of these basic services. So for example, when you create SQS message queues, there are multiple servers and built-in redundancy behind the scenes. When you post a message to a queue, that message is replicated across multiple machines so that your messages are always going to be properly stored and available for processing from the queue. Similarly, behind the scenes with Amazon S3, you store your object once. that object is stored, and at the point when that storage request completes and you receive a success acknowledgement, we've already made multiple copies of your data, and we're storing it with 11 nines of durability. Amazon SimpleDB has a similar degree of redundancy behind the scenes, as does the relational database service when used in the multi-availability zone or multi-AZ mode. In other situations, when you're using EC2, we're giving you some basic tools and features which you then need to combine in different ways to build systems that are both fault tolerant and highly available. These are things that we'll discuss over the course of this webinar, including things like availability zones, elastic IP addresses, elastic block storage, and so forth. I think it's really important as you think about and hear about these different services and think about how you're going to put them to use in your own architecture, there's definitely some trade-offs that you need to make. There's a continuum that goes from a very, very simple system with a single server and very, very little in the way of fault tolerance to a very, very complex system that has a high degree of redundancy, automated failover, and so forth, and a very, very quick time to recovery. You need to trade off things like your design budget, your implementation budget, your operational budget, versus the complexity that you are able to engineer into the system and the amount and the time that you desire for recovery. So different systems will have different degrees of criticality, and you need to take that into account as you're designing and saying what is the level of complexity that is worthwhile for this system. Let's take a quick refresh look at the various components of Amazon EC2. At the outermost level, we have the concept of a region. We have 5 different AWS regions in different locations around the world. The regions are subdivided into separate functional areas we call availability zones, and we encourage you to deploy different EC2 instances across different zones within a region for fault tolerance. Central to this diagram is the concept of the EC2 instance for doing your processing. When you launch your EC2 instances, you have your choice of 2 different types of storage. You have the ephemeral storage, which is storage attached to the EC2 instance, and with a lifetime that is the same as the instance. When you launch the instance, you get the storage. When the instance goes away, so does the storage. You also have the ability to create what are called elastic block storage, or EBS volumes. These volumes can range in size from a gigabyte up to a terabyte. They exist within a single availability zone, just like a particular EC2 instance. And they have a lifetime that's separate and distinct from that of any particular EC2 instance. Use EBS to create snapshots, which are point-in-time backups. You create those snapshots. They're stored with high durability in Amazon S3. You can later use those snapshots to recreate the volume contents in the same availability zone or in a different availability zone in the same region. On the network side, several important concepts. First, you have the ability to use security groups to control access to your EC2 instances. You have the ability to create elastic IP addresses and to map those to any EC2 instance in a particular region. An elastic IP address is specific to an individual AWS region. You also have the elastic load balancing feature that allows you to spread an incoming traffic load across any number of EC2 instances within a region. You are certainly familiar with the concept of the AMI, the Amazon Machine Image. Basically, that is your boot disk, which is pre-configured with your operating system, your applications, your development tools, and so forth, and used to boot up your EC2 instance. Operationally, your EC2 instances report various metrics such as CPU load, disk load, and network load to CloudWatch. Those metrics are stored at either 5-minute or 1-minute intervals, depending on the degree of monitoring that you've opted in for. You can access those metrics through the AWS Management Console, and you can also use those to drive auto-scaling, where you will bring in additional EC2 instances as needed to handle a traffic load, use the auto-scaling alarms to raise or lower the number of instances as needed. So important things to think about with EC2. I like to think of the AMI as really a set of packaged and reusable functionality. And I like to encourage people to think in terms of putting all the necessary parts into that AMI, getting it set up, getting it fully configured, and then as we'll talk about later, making that AMI as self-contained and as ready to run as possible. You have a number of choices of statically building AMIs, making them more dynamic, making them more configurable at setup or launch time, and we'll cover some of those options as well. When you think of storage, we talked about the on-instance or ephemeral storage, and with these disks, the lifetime is tied to the instance lifetime. And these have an AFR, which is short for annual failure rate, that's similar to a standard hard disk, which is generally about 5% of the drives in a given population will fail per year. The EBS volumes have a lifetime independent of any particular EC2 instance, and there is redundancy behind the scenes of an EBS volume. So when you store to EBS, your data is stored with a degree of redundancy. That redundancy is specific to a particular availability zone. And because of this redundancy, a particular EBS volume has an annual failure rate that is anywhere between about 0.1% and 0.5%. You generally want to think of your architecture in terms of logical volumes and logical mappings to different EC2 instances. And so as you design that architecture, you need to actually think about how am I going to map my volumes that a particular instance needs to the particular instance that happens to be running, serving a particular role. We do, of course, encourage you to use EBS snapshot backups and to have a regular backup cycle, a labeling methodology, and so forth, so that you not only do you back up your data, that you have a good way to track the last time your data was backed up, and to find the proper data to use in any kind of recovery situation. So elastic IP addresses, you can map those to any EC2 instance within a given region. The general way that you will think about these is that you will use an elastic IP address as effectively a logical endpoint, which you then map to the physical endpoint, being a particular EC2 instance, based on the instance that's serving in a particular role at a given time. The IP addresses can be easily detached from a failed instance and then mapped to a replacement, and generally that switchover takes somewhere less than a minute to accomplish. Very, very important is our auto-scaling feature, and there's two separate ways to use this. One that's obvious, and a second that might be a little bit less so. The first way to use auto-scaling is you use this to actually respond to changing conditions by adding or terminating EC2 instances. You do this by creating some CloudWatch alarms, using those alarms to actually initiate auto-scaling actions such as a scale-up or a scale-down action. That's kind of the obvious and we might think of as traditional way to use auto-scaling. The second way is to use auto-scaling to maintain a fixed number of instances. So you do this by simply creating the auto-scaling group, and you then set both the minimum and the maximum number of instances you'd like to run in that group to the same number. So if in your architecture you always need to have 2 instances of a particular kind of AMI running, you'd simply configure that constant number into the group. What this means is that once you've set up this fixed number of instances, that auto-scaling group will automatically perform health checks on those instances. If it finds them to be unhealthy, if they're not responding to pings or returning error conditions as you configure, the auto-scaling will automatically take care of taking those failed instances out of the group and replace them with healthy instances. When you think about fault tolerance, we also encourage you to think about the EC2 reserved instances, which guarantee capacity for you when you need it in a failover situation, and also give you a lower price for your hourly consumption of EC2. Now, CloudWatch alarms are a relatively new feature of CloudWatch, and it's something that we do encourage you to study and incorporate into your systems. The idea is that after we have your instances, your EBS volumes, and so forth, reporting metrics to CloudWatch, those metrics are stored at either 5 or 1 minute intervals, you can then use alarms, and you can create these alarms either programmatically from the command line or through the console. You can use these alarms to define various conditions that you would like to detect and then be notified of. So you can go to the console, you can select metrics on either individual instances or on groups or categories of instances, assign names and descriptions, and then thresholds to the alarm. The threshold can be a comparison, and then a percentage value, and then a duration. And so based on that, the metrics and your defined alarm, if an alarm fires, it can then initiate a notification, which you can then use to initiate auto-scaling, fire off an alert to you, page you, and so forth. Elastic load balancing, a critical feature in a fault-tolerant application. Think of elastic load balancing as the way to distribute incoming traffic across multiple EC2 instances. And again, this is configurable with the set of health checks, and the elastic load balancing that you set up will only route traffic to your healthy instances. You can use elastic load balancing in conjunction with auto-scaling. The auto-scaling has the ability to add additional instances to an elastic load balancer as they're brought online, and to remove instances from the load balancer as they're terminated. So elastic load balancing, auto-scaling work fine independently, work even better when you put them together. Now let's talk about a little bit about both regions and availability zones. Regions are a geographic concept, and we currently have 5 separate AWS regions. We have regions on the east and west coast of the US. We have a region in Europe, currently in Ireland, and we have a pair of regions in Asia Pacific, both in Singapore and Tokyo. When you choose to either do some processing or some storage, you always get to choose explicitly which of the regions you address your requests to. And we never migrate functionality or data between regions. The regions are totally separate and distinct. Within the regions, we break the regions down further into what we call AZs, or availability zones. And a given region will have anywhere between currently 2 and 4 or 5 availability zones. So what are the characteristics of availability zones, and what advice do we have to offer? So as you might know, availability zones are distinct physical locations. You could think of each AZ in a region as really a separate building or a separate data center. We have low latency network connections between the availability zones in a given region, and each of these AZs has independent power, cooling, network connectivity, and security. We recommend, as you'll see in my next slide, that you always partition complete application stacks across 2 or more availability zones within a region. We also encourage you to use elastic load balancing across these instances to spread your traffic across multiple availability zones in the same region. The idea being that you want to build your application such that if there is a problem in one AZ, that you have capacity and functionality in another AZ ready to take over for you. So here's a picture that shows you the proper use of multiple availability zones for your application. We have incoming requests at the bottom. Those requests hit the elastic load balancer. That elastic load balancer is aware of complete application stacks, or really aware of the web server, because it's going to be sending traffic to the web server. It's aware of the web servers in multiple availability zones inside of the region. The load balancer is always performing health checks to make sure it's able to reach the server in the region. So I should say a word or two about health checks. When you set up your load balancer, you get to include a URL that load balancer can effectively ping on the instance, and that URL has the opportunity to return a code that either says I'm healthy, or it can return a code that says I'm not healthy, or it can simply fail to respond, which also would mean that it's not healthy. The load balancer uses these health checks to make sure that it's only routing traffic to instances that are alive and up and running and able to serve. So per this diagram, we recommend that you deploy complete application stacks in 2 or more availability zones. So a complete application stack in a traditional multi-tier architecture would be a web server, an application server, a database server. Now, in this picture, I do have multiple copies of RDS shown here. What I'm really trying to convey is the fact that with RDS, which is the relational database service, you would generally use that in what we call the multi-AZ model, where there is both a primary and a secondary, and RDS will automatically take care of keeping the primary and the secondary healthy. If the primary fails, it will then make the secondary into the primary, launch a new secondary, make sure that we re-replicate the data, and so forth. So that this diagram, I think, is really key, and it shows you that you want each availability zone to have enough functionality to run the entire application. So we've received a number of questions about the proper ways to use regions and how to kind of think about regions as you architect your application. So the regions are functionally separate. They generally have we are working to make sure that we have the same AWS services in every region. Generally what we'll do when we roll out new AWS services, they will be in beta testing in a single region, and then as that beta test matures and progresses, we will then roll out that same functionality to the other regions. So they're functionally separate. Every region is composed of 2 or more availability zones, and the regions are connected to each other via the public internet. So you'll generally use regions for a couple different reasons. You will use them to have your functionality geographically close to your customers. So if you have customers mostly located in Asia, you could choose to use our Singapore or our Tokyo regions. If most of your customers are in the US, perhaps use the US East or US West regions. And also our customers sometimes make choices of regions based on their need to comply with national laws and practices. We do generally recommend that when you try to build your application, you can definitely build a highly available application within a single region by the use of multiple availability zones. Okay, and with that, I'd like to turn things over to my colleague Attila, and Attila is going to take you through our architectural guidance.
One important principle when you kind of take a step back and look at your architecture and want to ensure that it's designed for failure or fault tolerant is to really avoid single points of failures. So why is this so important? Well, clearly, if any component that is a single point of failure were to fail, it brings the entire system with it. So that's typically not acceptable and not what we want. So the guidance is that let's assume that everything can fail. A drive, a computer, the network, whatever the component or its function is, let's assume it could fail. So and then take a step back and design backwards from it. So look at your architecture and identify the components there, possibly a front end, an application layer, a database layer, and so on, and ask yourself, well, what happens if this component were to fail? And once you identify a single point of failure, basically if your answer to that question is, well, if that component fails, my entire system is down, it's time to put some redundancy in place. And the idea here is that with redundancy, you're able to replace or shift traffic or shift load over to the redundant healthy system while the failed system is either being fixed or being replaced. So the overall goal here is that the application or the system should continue to function, possibly in some kind of degraded mode where it's not working at 100% of the feature set, or not all components are fully working, but at least that the base functionality is in place. So that's the idea here. So if anything fails, really there should be no impact to your customers as much as possible, at least as far as the core functionality is concerned. With that comes the design of your recovery process. So let's say we identified these points of failures, we have redundancy in place. Now let's assume one of these components actually failed. What is there in place to recover from that? And we'll talk about a couple of the mechanisms in just a moment. The point I want to make right here is that it's critical to basically practice bringing up replacements, restoring from backup, and being really comfortable with that procedure. Like the last thing you want to happen is something fails or some disaster strikes and you're unsure about the process or don't have automation in place to get the system back up. And Jeff talked about this earlier. Really, Amazon Web Services gives the tools and the building blocks that allow you to trade off the business need for high availability versus the cost in infrastructure. So clearly, if you as you approach higher availability, your cost will also increase. And for some applications, it might be more important to be as cost-effective or as cheap as possible. Well, in which case, it could well be a business decision to trade off high availability. In other cases, if you have mission-critical systems, it will probably not be acceptable to trade off high availability, and the cost also will increase. Again, summary is that the tools and the functionality pieces that we discussed here are there to give you a choice, so you can pick the right mixture and build the right level of high availability into your application. All right, so let's take a look at some of those building blocks. I think Jeff did a great job introducing the concepts already. So again, what's really important here is the building block that we call elastic IP address. And why is that important? Well, it gives you a public IP address that you can map to any of your running instances in the region. So if there is a failure with any of the instances, you can take the elastic IP address that is pointing to that instance and map it to a replacement instance. Now, that instance can either be running already, kind of like a hot standby, or it could be something that you bring up and within just a few minutes, the instance will be up and running, and at that point you could move the elastic IP address to the new instance. Again, this is a great example where, if you put a hot standby in place, the cost is higher, and if you put a logic in place to launch a replacement instance quickly, then you might have just a few minutes of downtime while the replacement instance is coming up, but you're saving quite a bit of money by not having to run the hot standby 24/7. So this again is just an example where there are choices that you need to make here. The use of multiple availability zones, again, that's really critical, and I can't emphasize enough the importance of designing your application such that it acts as an isolated stack in each of the availability zones. Just to make the point clear, you can also get this really wrong where you have a lot of crosstalk between different availability zones, for example, by placing all your front ends into one availability zone and all your kind of application servers or database systems in the other availability zone. Well, that's the wrong way of doing this, right? So what you want to do is that basically have independent stacks in each of the zones, meaning all critical systems that are required to make your system work need to be present in the zone, so that if any part of your system in one zone, or if even the entire zone become unavailable, the system continues to run because the isolated stack now is able to handle all the traffic. What's also important here is a capacity consideration. So if you lay out your system so that one or multiple availability zones can take over in case there is a failure in one of the availability zones, you have to plan your capacity accordingly. If you, for example, use 3 availability zones, then each of the zones cannot run at higher utilization than roughly 66%. Because if one of the zones were to fail, then well, 1/3 of your traffic would have to be absorbed by the other 2 zones. So their 66% utilization will go up to 99, and this is talking high already. You probably don't want to push the system this high. So again, use the availability zones, set up independent stacks, and make sure you use them correctly. This brings up the point of how to replicate data across multiple AZs, and there are a couple of ways of doing it. So if you have a database, for example, you can set up slaving or replication into a database installation in the other AZ. Another example is the Amazon Relational Data Services multi-AZ mode, which basically, as Jeff describes, puts a master and a replica in different availability zones. And depending on which application or which system you're using, there might be other methods of replicating data across AZs. The high-level point here is make sure that your data is not only present in a single kind of location that is not sufficiently redundant. So don't ever have your critical data just exist on a single on-instance store or on an EBS drive without snapshots, for example. The next point here is about the use of monitoring. Clearly, you can't really respond well to failures or to issues if your system doesn't pick it up. So what we offer is Amazon CloudWatch, our monitoring system. That's not to say that you must use Amazon CloudWatch. If you have existing monitoring systems that you're happy with, you can very well bring these to Amazon Web Services or monitor your EC2 instances with that. What's critical there, though, is that you're able to respond, and ideally in an automated manner, so that scripts fire or the right actions take place to put replacements in place, and so on. Now, if you use CloudWatch, of course, you get some nice synergies with some of our other services like auto-scaling and elastic load balancing. Using Elastic Block Store, that's another good practice. So if you consider the options that you have for an EC2 instance, well, there is the on-instance store or spindle, which has an annual failure rate of about 5%, which is that of a standard hard disk. Or you have Elastic Block Store, which is about the order of magnitude more durable. So we would certainly recommend using EBS for some of the critical data, plus taking snapshots of your data in EBS. These snapshots allow you to restore back to the time the snapshot was taken, and you can create new volumes from the snapshot in any AZ of the region. So this is also, using EBS snapshots, is also a viable way to move volumes across availability zones in a region if that were necessary. This drawing here is an example of a fault-tolerant architecture on EC2. What you see here is there is EC2 instance A, which is the master instance. Think of this as a database, for example, or some system where the master-slave concept applies. You have at the very top a elastic IP that's behind the DNS entry for yourwebsite.com, pointing to EC2 instance A. And at the bottom left, you have basically two EBS volumes. One is the data volume for the database, and the other is a log volume that basically keeps track of what's happening in the system. So instance A is serving all the traffic and is working with its own EBS volumes. Now, replication is in place to replicate data to a second EC2 instance, which is called instance B here. There is a slave, a database slave running on that instance, and that instance has its own EBS data volume that it writes to. So now let's take a look at what happens if there is a failure. Well, EC2 instance A would become unavailable. Of course, as a result, replication would stop, and reading and writing from the EBS volumes would stop. And at this point, your monitoring system would detect this. And what you can do is basically, in an automated, scripted way, you can remap your elastic IP address that's sitting behind the DNS entry for yourwebsite.com, make that now point to EC2 instance B. And EC2 instance B would then assume to be the master, as it's noticed that primary master has gone away. And it will then continue to write to the EBS log volume, which also can be mapped to this new instance now. So the point here is failures to an instance can be detected, and there can be orchestration, automation in place to basically remedy this. What's nice about this example here is, well, your clients will be interacting with the DNS name, yourwebsite.com, and from a client perspective, there was no change at all in any of your infrastructure. So there's no change in DNS. There's just a basically remapping of the elastic IP, which now routes to a new instance. All right, so now this was an example of two EC2 instances possibly in the same availability zone. Now in the next example here, let's look at an architecture of how this could look like between availability zones. So the setup looks really similar to the slide prior, with the exception of the white box, which denotes the availability zone now. Also note that logs are now captured in Amazon SimpleDB. Amazon SimpleDB is available to any location, not just within the availability zone. So if we want the ability to switch logging from one availability zone to the other, we want a system that can accommodate that easily. So here again, we have instance A, which is the master, instance B, which is the slave, and replication between them. So let's take a look at what happens when there is an issue in the availability zone. Well, the availability zone will disappear. Replication will stop the function, and monitoring would pick this up basically, and you would take the elastic IP, remap it to the instance B now. And note this very important nuance here. The elastic IP address actually is a regional concept. So if you allocate an elastic IP, you would specify which region you want it in. And it is possible to map that elastic IP address to any of your running instances in that region. So that's kind of a core concept here. And see what happened to Amazon SimpleDB. Well, as instance B assumed the master role, it knew that it needed to log to SimpleDB, and it will just do that. And once you analyze logs, you may not even notice that there was such a switch over. So it's a nice example of how this could be done. The opposite of a loosely coupled system obviously is a tightly coupled system, and tightly coupled systems are fairly brittle. If any of the pieces or any of the components have failures in a tightly coupled system, again, the entire system goes down. So loosely coupled systems give you higher availability and more stability, and you have choices around running your system possibly in degraded mode, or at least if there's a failure, then the remaining 90x% of your system can still be doing useful work. So the principle around building loosely coupled systems is to design independent components that are really exposed like a black box, that have interfaces that are well known, and other components talk to that interface. So on the right, you see a star-looking diagram here, and this is just a quick story on this one. This is a Amazon internal tool that shows you dependent services that are called every time you make a request of the Amazon.com website. So if you point your browser to the Amazon.com website, the component that's rendering the HTML will actually consult all these different services before the page is put together, or as the page is put together. Such services might, for example, be, well, who is the customer, what's the price for this item, customers who bought this also bought X, Y, and Z. These are the 5 objects or 5 products that I last looked at. Well, if you take a step back behind the scenes of the Amazon webpage, you can very well imagine what these components would look like. And clearly there are components that are more critical that we have designed with higher availability, and then there are components that are possibly less critical. For example, one component that might be less critical in a online retail application is the widget that's showing the last 5 objects that you looked at. Clearly, as the customer navigates the site and looks at the next couple of items, anyway, that the data will quickly be rebuilt. However, the component that's processing orders or keeping inventory clearly has a much different bar of high availability and fault tolerance. So again, an example where a business need can dictate or would dictate the investment that is made here. What's further interesting, or a nice property of these loosely coupled systems, is that you can load balance and scale these clusters independently. So you can bring in more machines into clusters that need it. You can treat each of these services as a subsystem, so to speak, which is load balanced independently. All right. At the very bottom, there is also a example of tight coupling, and what I want to introduce here is an example where SQS, the simple queuing service, could be helpful. So in the tight coupling example here, we have controller A, B, and C, and they all directly speak to each other. So if there is a failure with any of the controllers, let's say controller B goes down, well, controller A can no longer function because it can't reach controller B. And controller C also is not working because nothing is talking to it. So with SQS, you can do this slightly differently, because SQS will be a great buffer between these controllers. And this is the drawing at the very bottom that's just faded in. So loose coupling using queues would bring in these green dots, or the queues that are depicted as green dots with a queue in it, between each of the controllers. So controller A will read from a queue and put its output back onto a queue, and controller B does the same, and so on. So in the example where controller B were to go down, well, controller A and controller C can still continue to do useful work. Of course, once the queue for controller C is empty, then at that point controller C will also just be sitting around. But hopefully that gives you enough time to bring controller B back up. This slide is about implementing elasticity, and you notice that's a keyword in many of our features and service names. So let's talk a little bit about why this is important in the context of high availability. Well, anytime you assume the health or the fixed location of a component, it makes you a little bit more dependent and less flexible. So the idea here with EC2 is that you should be able to bring up replacement instances or additional instances that help you shoulder the load. So the moment you assume health or a fixed location, it will make that a lot more difficult. So rather than hard coding IP addresses, make use of elastic IP addresses that you can remap. Or if you know that you're going to work with more than one instances, look at load balancing, so you can add and remove instances behind the load balancer. Now, also think about that launches and reboots could occur more frequently. So if you bring replacement instances or additional instances into your application architecture, then dealing with these relaunches and reboots should be something that doesn't break the application. And, typically that's not very hard. Think about how the Elastic Load Balancer has a health check that's basically making sure your instances is in good shape before sending traffic to it. Well, that concept kind of applies to, could possibly apply to other areas as well. So keep that in mind. And really a good way to bring up these instances in an elastic way is to have the bootstrap logic of your instance ask the question, who am I and what do I need to do in this deployment? So for example, you could be launching an additional front end because your web traffic has increased. So what you don't want to do is log into that instance, start installing Apache, start configuring it. No, you want this to be automatic. So there's a good way to, we actually have a slide later on that talks about this in more detail. What's a good way is to basically have all this automated. Tell the instance what is its role in the architecture, and then have the instance automatically configure itself. So basically enable dynamic configuration and bootstrapping of that instance. One good way to keep some of the deployment state. Now, one question that will come up here is, well, okay, how do I do this? Where do I store my state? How do I tell my instance what it should do? Or where are the elastic IPs? Which load balancer should it use, and so on? Well, the answer is SimpleDB is a great place to store this kind of deployment metadata, and it's extremely cost-effective as well. You likely will not come out of the free tier for your deployment metadata. Plus, it's accessible from all your instances, plus from your home office. So, definitely a great place to put this. Plus, it can be modified by any of the instances or entities of your architecture. So, the way this could look like as well, your instance comes up, it checks what it needs to install, it runs the correct script, and then looks at SimpleDB for configuration information such as which application layer to use, which bucket might contain images, and so on. Now, the last points on here is the use of autoscaling and elastic load balancing. I think Jeff covered this in quite some detail already. Basically, autoscaling is a great tool that integrates natively with CloudWatch, our monitoring system, to either scale up and scale down, meaning start or stop instances if traffic pattern changes, or replace instances that are no longer healthy. And load balancing, again, is a great tool to achieve higher availability because it has health checks built in. It will only send traffic to your healthy instances. All right, with that, I'd like to hand over to Max, who will speak a little bit more about hints and tips.
Great, thanks, Attila. So one of the first things that we're going to talk about here is building on this idea of the self-managed EC2 instances that Attila was talking about. And there's a couple different starting points you can go with this. You could start off using fixed or pre-configured AMIs, and then going on and doing additional configuration on top of that. Or you could start with fully dynamic AMIs, where you're going from a base image and installing all the software you need and all the application you need on top of that. So one of the things that you can do when these things start up is take advantage of things like Cloud Init and scripting, whether you're using Python, Ruby, or Shell scripts. And any Amazon Linux and all the newer Ubuntu AMIs take advantage of that. For Windows, you can also take advantage of PowerShell and the .NET SDK to automate a lot of this. And then, of course, there are other third-party tools such as Boto, Capistrano, or RightScale that also support this idea of a self-managed or self-configured instance. You could have the AMI ask as it boots, who and what am I? And you could ask that in a couple different places. You could look in the user data, or you could query the tags themselves for that information. Other things that you can do here is set the role so that it can say, I'm actually an app server for application X, and then go query the information it needs to be able to pull down and install whatever packages it needs to be that app server, and then point its configuration to that appropriate application and database server, etc. Tools such as Puppet and Chef are very handy for being able to dynamically configure and install applications on top of instances. Other things that you can do as you come in here and install or update application code is look in a code repository such as Git or CVS, or you could store that code in S3 and have the application pull it down either just on boot, or you could even script in the logic for it to check that periodically and do updates as it goes along. So maybe you want to have it check for updates every hour or so. Other things you can do is attach different EBS volumes to the instance, and they don't all have to be just boot or data volumes. You could also do things like have a snapshot of all the files you need to install the software. So you might just have that EBS volume attached during the boot and configuration time, and then once you've installed all the software you need, you can then detach that EBS volume. And that may be a little faster than trying to go and pull the software you need dynamically at runtime. Other things you can do is take advantage of elastic IP addresses. So an interesting fact about EIPs is that if you resolve the DNS name of an EIP from within EC2, you'll get the 10 dot address. And if you resolve that same name from off of EC2, you'll actually get the public IP of it. So one thing you can do is use the DNS name of the elastic IP address in connection strings so that you get some insulation should your instance fail. You could then point your EIP to a new instance, and your application logic wouldn't have to change too much. You could also take advantage of tags to do things like set what state the instance is in. Or you could take advantage of it to do things like say, I'm actually a dev instance or a production instance. And finally, you could do some health checks. And one of the things that you should do as you go online is do things like register this instance into server pools. So whether you're taking advantage of things like SDB or Active Directory, you can have the instance tell the rest of the system that it's now available to process data. Other things you should do is add some abstraction. So when you're talking about how you think of your system, you really shouldn't think about it in physical terms. You should abstract it to the maximum amount possible. So one thing that would be very useful is to take advantage of services whenever possible. So things like SNS and maybe SQS. Also things that would be useful are things like worrying about the machine image in the sense of here's the Puppet or Chef configuration file that's going to be applied to it. That helps when you're dealing with auto-scaling environments. The other thing that becomes very useful is if you build the entire system out of a CloudFormation template. Because then if you need to recover or you need to deploy additional instances, such as an additional test instance or additional production instance in a new region, you can simply adjust the CloudFormation template and launch it and not have to worry about all the details so much. And finally, since we're running out of time, one thing that we'll want to do is talk about using a chaos monkey. So Netflix had a really nice write-up about this concept that they have, and it's actually a tool that they use internally. But it's something that anyone can do. And the idea is really design your systems so that you can randomly kill any aspect of it, and it will simply recover. And the chaos monkey is a way to automate that. So you could go in and decide that you're going to have your system and randomly kill off an instance, say an app server or a web server, or change the security groups and see how your system adapts to that change. And it's much better if you can do that in a controlled manner than it is if you just have to learn what your system's going to do during a failure. And finally, you don't need a tool at all to automate this because you could simply use the AWS Management Console to go ahead and make those adjustments. So there are additional resources, and most of what we talked about is available at the AWS Architecture Center. And here you'll find different white papers talking about architecture, fault tolerance, and different best practices. And there's also a link that is aws.amazon.com white papers that has a list of all the white papers that are available from AWS. And finally, there's premium support, which is available. And I would suggest that customers go ahead and get premium support. At the bronze level, it's only $49 a month, and that gives you access to actual paid support, the ability to open up a ticket and get help, whether it's basic advice or it's just troubleshooting. Customers should take advantage of premium support. Not everyone's going to need the highest levels, but at the platinum level, you do get access to things like a dedicated technical account manager and access to the AWS Solution Architects for advice. And of course, you can always learn more at our premium support site. At that, then we'll go ahead and open up the presentation for any questions that might be there at this time.
Question from Eric. He says, why would I point mywebsite.com to an EIP if the Elastic IP can only be associated with one instance? Then I'm lacking load balancing, right?
Okay, Attila, can you take that one?
Yeah, absolutely. Great observation, and that's actually correct. So if you take only a single IP address and you point your DNS to that single IP address, then indeed you're only sending traffic to a single instance. The alternate approach there to use load balancing, which is definitely recommended, is to either use ELB directly, which is the easiest way to do it, in which case ELB gives you a DNS name, and you would configure a CNAME in your DNS and point to the ELB that way. And then you get all the load balancing of the ELB service. Alternatively, you could continue to go with this single load balancer or single IP and point it to an instance that's running a software load balancer that is not quite as highly available, but that's a choice that you can make if you want to distribute the traffic amongst multiple instances behind the load balancer instance. Yeah, great observation. Thanks for the question.
Great. Thanks, Attila. The next question, Max, maybe you want to fill this one. Is how would the fault-tolerant architecture operate in the case of a network partition instead of an instance failure? And he's basically referring to the slide we were just on in terms of the mywebsite.com. I think when he's talking about the fault-tolerant architecture.
So if by a network partition, we're talking about failure of a network segment?
I think that's the right assumption.
Okay. So if you're taking advantage of something like elastic load balancing, and you've taken advantage of a multi-AZ deployment where typically you might have, say, 2 web servers, 2 app servers, 2 database servers. In the multi-AZ deployment where you've deployed half of that in one AZ and the other half in another AZ, then should an entire AZ become unavailable for, say, some network routing issue, then the Elastic Load Balancer would simply detect that that instance in that AZ is unavailable and route all the traffic to the other AZ. And if you've added auto-scaling to that for your web and app tier, then the environment would add additional servers to meet the demand load that you have running.
Great, thanks. On this question, Till, this might be a good one for you. It says, with fault-tolerant architecture on EC2, after the first instance fails and you fail to the second instance, how do you recommend moving past this point? Do you bring up a third instance and demote it to the slave? So I think what he's really getting at here is once you fail to your other stack in another AZ, what do you do to get high availability again?
Yeah, great question. Because the moment your primary fails and you do this failover like we talked about, you're actually, for a brief amount of time, you're running in non-redundant mode. So the goal here would be to, as quickly as possible, bring up a working stack again. If you just had a single instance failure, it might be easier to repair the old stack by just bringing up, let's say, the new front end that failed previously. If there is a larger problem, then you would have to bootstrap an entirely new stack in a different availability zone. Again, and this is where some of the best practices we spoke about dynamic configuration, making sure the instance asks about what role it needs to take and build itself out. So within just a few minutes, you should be able to build a entirely new application stack in another availability zone. Yeah, great question. Thank you.
And on behalf of Amazon Web Services, again, just thank you, and I would hope that you found the session today informative.